This lecture will discuss application of linked list. We'll take one specific example. Rest of the applications I have left as an assignment for you. So one of the applications of linked list is that we can add two polynomials where each polynomial is represented using a linked list. So a polynomial, it has two components. One is your coefficient and the other one is your exponent. And then there is a chain, in the sense you have different terms in the polynomial with varying degrees. So every degree occurs once, and normally we represent a polynomial in the decreasing order of the exponent values. So 3, 2, 1 in this case and 2, 1, 0 in this case. So when we have to do polynomial addition using linked list, the first thing we do is we define the structure for polynomial. So in each node of the polynomial, we store a coefficient, an exponent, and a next point. So the other way of implementing polynomials is using arrays. So an easy way of representing a polynomial using an array is that we store the coefficient of a particular degree in the location specified by that. For example, if I have 5x3, this will be stored in the location 3 of the array. So 5 will be stored there. So since I'm accessing A3, suppose, for the array, that means it is the exponent value is 3. But if you see, for polynomials which are like let's say 5x to the power 31 and then 2x square plus x, if I use a static array of size, let's say 31, I will be storing only 3 terms in the array, which will waste a lot of space. So an ideal replacement is a linked list where you store nodes equal to the number of terms in your polynomial. So this is how my P and Q will look like once I represent them using my polynomial. So as the user enters the polynomial, you take two values instead of one now. You take the coefficient and the exponent in decreasing order of the exponent, so that we know our polynomial is stored in descending order of the exponent value. So we'll have two polynomials like this. Then we have to add them. This is the basic operation, add or subtract, and then we can also see how we can multiply them. So when you add, you have P pointing to 5, the first node, 5 is the coefficient, and Q pointing to 2, which is the first node of the second polynomial. So I compare the exponent values. I can add only if the degrees or the exponent is same. Okay, so if you see the first nodes, the exponent is different, so I cannot add. Okay, I cannot add 5x cubed plus 2x squared. So when there is a mismatch in the exponent value, I increment the pointer. But which pointer will I increment? 5 to the power x3, if there is the exponent in the next polynomial is less than this exponent value, that means there is no degree 3 in cube. As you can see, there is no degree 3. So I can safely put 5x cubed in my solution. So I will send this to my resultant linked list and I'll increment this pointer here, and this pointer will stay. In the next round, when I compare the exponents, I'll see a match between the two and I'll add the coefficients. So I'll get 4x squared and I'll send that to my resultant linked list. So what do I mean by sending to the resultant linked list? I have declared another start pointer which will be used to add a node in the linked list at the end. So as I get a term here, I send it there. It will be added just like we add a node to the linked list. Once there is a match and I'm adding 2x square and 2x square to get 4x square, I have to increment both the pointers because I've used these two nodes already. So next is here and the Q pointer will be here. Okay, again there's an exponent match, so I'll get 4x and I'll send that 4x to my resultant linked list. Then I'll increment this. So this goes to null, and when I increment this, this still has one more term. Once one of the two polynomials hits a null, that means you can add the rest of the nodes of the second polynomial straight away to your answer. Okay. So this is a simple explanation here. I want you to go through. This is a page. I'll send you the link later for this page. I hope you are getting all of this in screen. So this is an example on Geeks for Geeks for polynomial addition. So if you see, this is how they are representing your polynomial. So they have used an example here. You can go through this. I'll show you the list version. So this is your list 1 and list 2. When you add, you will obviously add the ones with the same exponent value, and if there is no match for 5x square here, you straight away put 5x square here in the resultant list. If you have a match, you add and you add. Okay, the node structure is coefficient, the power or the exponent value, and the address of the next node. So let's go down here. Okay, so this is how they have coded this. So the code, if your linked list code is working, you can straight away replicate your program, change the structure, and after you change the structure, you have to do create node. What does create node look like if you're doing a polynomial addition? Again, here the first line, you are adding, you're creating first of all, you're creating a malloc, you're creating a node, then you're putting the coefficient and the power which you're passing in the function here, and it is also passing a pointer. So that way temp, it is putting, if you see, it's a double pointer, it is a pointer to a pointer, so it's passing the address of start probably, so that you can modify it once you add a node. So after you create the node, R2 coefficient is x and y, this is else in case there's already a list created, you create the next node in the next field, and then you put the next field to null. I think they have done it the opposite way, in the sense descending order. So let's straight away go to addition. I want to discuss this. You can go through and see what implementation they have used here. So polynomial add, you send the start pointer of polynomial 1, polynomial 2, and this is your resultant. So while if one of the two hits null, you exit and you put the rest of the nodes of the second list in the resultant linked list. So while both of them are not equal to null, if the power of 1 is greater than the power of 2, then you have to straight away increment your poly 1. Okay, so, and you have to copy these values to send to the resultant linked list. So in the poly is your resultant power, you put the power for polynomial 1 and the coefficient, and you increment your poly 1, because there is no comparative term in the second polynomial. So if this polynomial second one is greater, for example, then you will do the other way around for polynomial 2. Okay, if both the polynomial numbers or the exponents or the powers in this case, they are the same, then you add the 2 here and you pass it to your polynomial. Okay, as well as the coefficient. So once you can call a separate create function for your resultant, or see how it's doing it here, polynomial to next, in the next field it is putting a new structure, then making polynomial point to polynomial to next. So it is pointing to the node it just created now, and then polynomial to next is null. So you're adding at the end of the linked list in this case. Now if you exit that while loop which said if both are not equal to null, in case one of them is null, you check which one is null. Have you hit the end of polynomial 1, or have you hit the end of polynomial 2? If you hit the end of polynomial 1, then you copy all the this is if you have hit the end of polynomial 2. So polynomial 1 to next is still not null. You copy all the values of polynomial 1 to your poly, and then it will get created at the end here. Otherwise, if polynomial 2 still has some nodes, you copy them and then It is just one node. You copy, create that, then the loop continues, okay, till it exits, and then you can display. So you can go through this program. It's on Geeks for Geeks for polynomial addition. So now multiplication is basically repeated addition. So once when we are multiplying two polynomials, what we do is we take the first term of the polynomial, multiply it with all the terms of the second polynomial, and whatever the resultant, we keep it aside. Then we multiply the second term of the first polynomial with the whole second polynomial, and then we add all these terms that we get together. Okay, so what we do in case of multiplication, if you don't have to implement that, that's a bit complicated, but you can see the logic goes like this. If you have P and Q, you copy Q to a temporary linked list. Now what you do is you take the first term of polynomial 1, multiply it with all these terms in the temporary linked list. Okay, so what you get is your first set of mm, uh, terms after multiplication by just one node of the first linked list. So you keep them there. Then what you do is you take the second term and you do the same and you add it. So the logic goes like this. So first we copy Q to a temporary list, then we multiply one node of P to each node in T and save it in T. Okay. Then we add polynomial, this T, the temporary one, to R. R is your resultant. So now this first set of terms that we got, it is in the resultant. Then we free this temporary again, okay, because this temporary has now changed. It's not Q, it is first term of P into Q. Then we move the pointer of P to the next one. Then again we copy all of your Q to temporary, again multiply the second term of P with all the terms in T, add this T to your resultant, and then free it, and then proceed till you hit the end of the first linked list. So I'll ask you to go through uh, the algorithm of multiplication of linked list, that is multiplication of polynomials using linked list. So this is one such example where you can see how your linked lists are used. You'll see later in your courses, for example, uh, when we talk of networks at our routers and switches, we have incoming packets, and the packets need to be processed to be sent to different links. So to process those, we put all these packets in a queue. Queue can be implemented using linked list. You have queues in your operating systems. You have queues in a printer where you print. When you send multiple print commands, your documents are queued in the linked list. So all these basically utilize your data structures like linked list, queues, and stats. So linked list is the basic data structure. It can be modified to act like a queue or a stack, which you'll see in the lectures to follow. So there are a lot more other applications which you can see. So this is part of your assignment 1. At least 5 solid practical applications of linked list you'll find, and you'll write them down in your assignment. Okay, so this is the end of the application. We'll continue with implementation of doubly linked list, circular linked list, and that will finish up the linked list topic, and then we'll proceed to recursion and stats after this. Continuing with our doubly linked list, this is the code for doubly linked list. There's not much difference you'll see when I run this code, but you'll see we'll discuss what are the changes that are there in doubly linked list with respect to singly linked list. As I've already discussed in my lecture, that there is an additional pointer in the doubly linked list, and whenever we do insert delete, we have to make sure that we are taking care of both the pointers. So especially when we are talking about the beginning and the end node, you have to set the back pointer for the first node to null, and you have to set the next pointer of the last node to null. Also, since in a doubly linked list you have the capacity to traverse in both directions, so you'll also see that I have implemented a reverse printing function in this case. Okay, so the program is the same like linked list. The first difference is that my structure has changed. Now I have a previous and a next field. Then I have added another function here, which is reverse printing. Rest everything is the same, just maybe a little modification with respect to how I'm handling positions. Okay, so let me first run this and then we'll see the output. Okay, so here we have, you want to create the list, enter the you want element and then print. So 5, like I discussed in the last uh, implementation of singly linked list, I have created the create list function, which is choice 1, as a function which only lets you create the first node if the list is empty. It is not required to have it separately, but just I have implemented it that way. So now I want to insert element, so enter position at which to insert, and now I can give any position where I want to insert, and I have mentioned 0 for last. So if I want to insert at the end, I have to put 0 for the position. So let's say I want to insert at position 2, I want to insert 10, and let's see what we have. We got 5 and 10. So now if I want to, I gave position 2, which was actually the last position. So let me again insert. Let's insert 15. Sorry, first let's put the position as 0, put the element as 15. So it should be the last element now. So 5, 10 and 15. So similarly, if you say delete, enter the position. Let's say I want to delete 10. So my 10 is deleted. Again, let's say delete, enter position 1, so my 5 is deleted. Then again, let's say delete, enter position, let's say enter the wrong position, 5, so position doesn't exist. So again, my list is still there. Delete, enter position, so this is position 1, and now if I print, my list is empty. So I can also delete a specific element. You see I have that as a choice here, which is choice number 6. So let's say we create a linked list again. Okay, there's some issue with this. Okay, let me I have probably written it such that I have to insert, I have to create the list first and then insert. Okay, create the list first, then insert. Let me insert 2-3 elements. Let's insert 4 elements. Insert position 4, 20, insert position 5, 25. So let's print it. So this is my linked list. Now I can delete at a specific position, which is my choice 6. So if you see, my 20 is at position 4. So enter the element you want to delete. I want to delete 20. I'm not doing it by position this time, so I'm doing it by element. So if you see, my 20 is gone now. Now we have the next choice of reverse printing. So my elements are 5, 10, 15, 25, and I can do 25, 15, 10, 5. I'm just printing it in reverse order. I'm not reversing the list. So you have the choice of traversing in the opposite direction, and that's how you can easily do a reverse in case of a doubly linked list. So let's exit here. I will run a similar code which I have for circular linked list. Okay, so before running into the code, let's first go over singly linked list, the circular singly linked list. So let me just zoom this here. Okay, so what is a circular linked list? A circular linked list is one where you have the single linked list as you know, and then instead of this last node here pointing to null, it is pointing back to the first node. And in case you have a doubly circular linked list, then you have two pointers, the last node pointing to the first node and the back pointer or the previous pointer of the first node pointing to the last node. So again, this is just similar to your singly and doubly linked list. The only difference is when you modify the first or the last element, you have to make sure that the pointers, in case of circular singly linked list, the last node should point to the first node, and in case of doubly circular linked list, the last node should point to the first node and the first node should also point to the last node. So when we do insertions and deletions, we take care of those. Okay. Then we also have another way of implementing this. The functions are going to be the same, just this extra step where you take care of the pointer. So I'll leave that as an exercise for you. The other implementation is to simplify, because when you traverse a circular linked list, what is the exit condition of your traversal loop? Normally in linked list we say start to next or while your temp to next is not equal to null. So here there is no null at the end. So temp to next is equal to start, so that's your exit condition. Sometimes it might become a little complicated, so what you can do, if you are allowed in your programming assignment or paper, only then you will use two pointers. You have the start pointer which points to the first node. You will maintain another pointer just like we maintain the start pointer, but this pointer is known as rear and it points to the last node. So when you update the last node, you will update the rear pointer. If you delete the last node, rear should point to the element, the node before it, and if you add something after the last node, the rear should be modified to point to that node. So just like we used to take care of start pointer separately, we have to take care of rear pointer separately in this case. So the only difference is that we have to update them accordingly. Okay. So let me go back to the circular linked list. It's not opening here. Let's try opening here. Okay, so this is your circular linked list. In case of circular linked list, I have just put some basic functions: create, insert, and delete element. Let me just zoom it. Okay, so let's see what difference we see in the implementation part. So create is same. Traverse, if you look at the traversal, if the start is null, you print list is empty. Otherwise, I have maintained a pointer which I copy start pointer in PTR, and my condition is while pointer to next is not equal to start, loop and then do whatever you want to do inside the loop. So that is the only difference that you will see in case of circular. And if you have a rear pointer, here instead of start in this line, you will use the rear pointer. So while your pointer to next is not equal to rear, you do what you want to do in the traversal loop and then you exit. So again, for finding the length, I have to go from start to end. Okay. So if you see, I have written it in the similar fashion, only the loop condition is different. Insert at a position. So only if the position is 1 does your start change here, which we have covered previously. And if the position is the last position, if you remember in this case, I have given 0 as the last position. So when you add the new node at the last position, Your previous is the last node of the existing linked list. In the next of previous, we put the new node, and in the next field of new node, we put start. Okay, here, so that we make this list circular. Okay, rest everything is the same. So again, delete if you're deleting the last node. And how would you know you are deleting the last node? So in case you are doing that, you will take care of the last pointer. So in the whatever the next field of the last pointer, it goes to the next field of the previous node. Okay, so let me run this. So create list. You will not be able to see whether it's circular or not, because uh, there's no way of showing you that I have maintained a circular list in this program. It's just the implementation. So insert 0 for last position, 4, so 1 and 4. Again, let's say insert at the end 5, so 1 4 5. So 5 is being connected back to 1. So if you want to delete an element, okay, it's enter your choice. I've inserted again, so let's insert 10. So now I have 1 4 5 10. Delete an element, choice 3. Enter the position at which item is to be deleted. So I'm doing it by position here. In doubly linked list, I had done it with position and with uh, the specific element. So I want to delete position 2, which is element 4, and I pressed the wrong key by mistake. So let's run it again. Create, insert, 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 and print. So 1 2 3 4 is my list. Delete by position. So I want to delete position 2. So element 2 should be deleted, and 2 is deleted. Okay, so rest you can add all the functions like we have done in singly linked list and doubly linked list. So print and exit. So this is your circular linked list. So similarly we have for doubly circular linked list. So if you go back here, let me open the doubly circular linked list as well. This is not the doubly circular, this is just the doubly linked list. So I wanted to show you the reverse in case of doubly linked list. So traverse in the reverse order. I want to just zoom it a bit. Okay, so this is my traverse here. So what am I doing? Just like a normal traversal, I am copying start to temp, while temp to next is not equal to null. Temp is equal to temp to next. So this will stop at the last node. When you leave this first while loop, you will be at the last node when you leave the blue while loop. But when you reach the pink while loop, which is highlighted here, your temp is pointing to the last node. So I want to print in the reverse direction. So I will write a similar loop, but instead of having temp is equal to temp to next, I'm doing temp is equal to temp to previous and printing the element. So temp to previous is not equal to null. I print the element in temp, then I make temp point to temp to previous, and once the loop uh, is done, you will stop when temp to previous is null, which means you will stop at the first node. If you remember, I have told you in case you are writing the loop like this, you have to add an additional print at the end. So this is your reverse traverse. So if you are doing these same programs for your doubly circular linked lists, so let's say this is your insert at position 0, which is the last position. So once you do all the pointer changes in a simple doubly linked list, after this you have to make this new node point to start, and you have to make the start node point back to new node. So you have to add just two more lines of code here. After doing all the changes in the pointers here, you have to add those two lines of code, which are two pointer changes that you are making, and your code will change to doubly circular linked list. Obviously you will also uh, decide whether you want to have separate start and rear pointer, or you just want to do with the start pointer. So a circular linked list structure will be the same. You have a previous, you have a next. There's no difference between a doubly linked list and a doubly circular linked list structure. The only difference is in the implementation and how you visualize your linked list in that case. So it's circular. So you have to make sure you make the changes accordingly, so that every time you make a change to your list, you make sure last node points to the first node and first node points to the last node. In case of doubly linked list, and if it's a singly linked list in circular, your last node points to the first node. That is one additional pointer change, one additional line of code. In all the functions that require it, you will do that and your program will be done. Okay, so with this we have wound up on this topic of linked lists. I am putting up an assignment for some basic things that I want you to do. There's only one programming code assignment, and rest are simple questions which you will be submitting in a week's time. So I'll give you some time to go through the lectures if you have not already, so that you can write a program and do that particular you have to do that particular function. So if you have already written a code on linked list, you just have to add one more function to your program, and you can see your output also. Okay, so this is the end of linked list. We'll start with recursion and stacks.